Good afternoon, everyone.
Good afternoon, sir.
And today is lecture number 2 of this heat treatment class. And today we're gonna discuss about different microstructures in steels. So since this is topic is basically on heat treatment, so as we have discussed in the earlier lecture that there are three
Hello,
means
sir.
by which, yes,
Sir, रामेश्वरी पात्र ଟିକେ add କରି
ask her to join again. I cannot able to see her. So as we have discussed in the previous class that there are three techniques by which we can improves the performance of a material, or you can say we can change the property of a material, right? So first one is that by changing the composition of a material, like we have pure metals. From pure metals we can make alloys out of that, and we can enhance the properties because each alloying element will have a definite role to play there, right? That is one part. And the part is by doing plastic deformation, because you understand when we do plastic deformation on a material, we are permanently deforming a material, right? We are generating lot of dislocations, lot of defects inside it, and sometimes we store energy into a material during plastic deformation, right? And due to which it can lead to strain hardening, or sometimes if you do annealing on it, we can get some fine grain structure that is called recrystallization, right? So that is another way to change the properties or performance of a material. And another one is the most important, that is heat treatment, right? So which we are mainly going to focus on, right? Heat treatment is a treatment basically given to the metals where we can improve the properties, or where we can change the performance of a material depending upon our requirement. But here we are not adding any kind of, basically it involves heating the metal or heating the alloy to a particular temperature and holding it, and finally cooling it at a different rates. So this is the main basis of heat treatment, right? So here we are not going to add any kind of alloying elements basically, unless until it is a chemical heat treatment. And we have seen we have three kinds of heat treatment. One is thermal heat treatment, chemical heat treatment, and thermomechanical heat treatment. So in this subject we basically concerned with two part. One is your thermal heat treatment and chemical heat treatment. We are not going to discuss about thermomechanical heat treatment. So you understand thermal heat treatment, it means it involves high temperature, right? We have to take the metal or alloy to a high temperature, then we have to hold the metal at a high temperature, and finally we have to different rate of cooling. We have to cool the sample at different rate, right? But today you can see this is the introduction part. Heat treatment is a technique where without doing change in composition or any plastic deformation, we can change the performance of material, which basically involves heat, which basically involves heat. You can write which basically involves heating, which basically involves heating the metal and alloys and cooling it at different cooling rates. Let me give an simple example, right?
Sir,
Suppose,
Rameshwari is requesting to join.
suppose I request everybody to please join in time. So suppose the best example of heat treatment I can give you is simple case. You take 0.8 weight percentage of carbon steel, which is an eutectoid steel, we know that. What you have to do, you do complete austenitizing this kind of steel. That means the entire steel is now having austenite grain, right? And we know that austenitizing temperature is fixed. That is fixed means that is at a high temperature range, right? So that everything will be austenite. And finally, what you do, cool it at different rates. Now we do cooling the steel at different rate or in different mediums. One is inside the furnace, for example. Inside the furnace means you are putting the sample and switching on the furnace, and you go to austenitizing temperature. After some times, you just switch off the furnace. That's all. You do not have to take out the sample from that. Second one is open air. You just take out the sample from the furnace. That is another. And another one is open air forced cooling. That means you can use a fan or any high speed coolers to cool it in outside the atmosphere, not inside the furnace. So that means the cooling rate is increasing. You can see inside the furnace means cooling rate will be very slow. Open air means cooling rate will be somewhat fast, and open air forced cooling means cooling rate will be somewhat more fast. Now, results in different microstructures, results in different mechanical properties, and results in different performance. So what happens? The steel is same, that is 0.88% is carbon steel, but upon different rate of cooling, we can get different microstructures. In the first case, when we are doing furnace cooling, we will get a coarse perlitic structure. Coarse perlitic structure here. And when we are doing open air cooling, we'll get fine perlite. But when we do open air forced cooling, we'll get more fine perlite. So we can understand initially we get a coarse perlite, we are getting fine perlite, and in the last case we are getting very fine perlite, right? That means what kind of properties has changed? The hardness and strength has increased slowly from here to here, then to here, right? So this is the way we do heat treatment of with different materials, right?
Sir, sir,
Yes,
sir,
yes.
in the open air forced cooling, we can also get martensite na, because fast cooling we are doing.
But just look at the composition. You
Yes,
people
yes.
look at the composition. I always, if you look into the iron carbon phase diagram, in iron carbon phase diagram, you always get equilibrium products, and martensite is never an equilibrium product. And you just see the composition of carbon.
Yes, sir,
And there
yes.
is no alloying elements are there. If alloying elements will be there and you are doing slow cooling, you can get a, or forced cooling, you can get a martensite. If you remember the effect of alloying element on TTT diagram, the nose of the seeker moves towards right.
Yes, sir, yes, sir.
Right? Okay, very good. We'll discuss that again. No need to worry about that. That is also there in your syllabus. We'll discuss that again. TTT diagram.
Sir, hardness of steel टा को जाए अधिक हबो?
Obviously, it increases from here to here to here. Finally, maximum hardness here because perlite are very, very fine here. Now it is okay.
Yes, sir.
Now structure property correlation example. I'll give you some good example where you can correlate structure property correlation. Okay, here the crystal structure changes by changing composition, example, and change in property. So best example I can give you, if you change the composition, you can change the properties, right? Or you can change the structure also. Just by changing the composition, you can change the structure, and just by changing the structure, you can change the property. For example, carbon steel and 18:8 stainless steel. Carbon steel only contains iron and carbon, but 18:8 stainless steel contain 18% chromium and 8% nickel. So what happens in carbon steel? We have ferrite structure, BCC, body centered cubic, right? But the moment you are going to stainless steel, it become FCC basically, because okay, it depends on the composition, but still you are getting, due to 8% of nickel, you are getting some FCC structure. Fine. So here crystal structure is getting changed, you can say. So by changing the composition, you can change the structure. And property also enhanced. The corrosion property will be more here. Oxidation property will be more here. The strength will be also more here. As compared to this one. Then another one, adding stabilizers to the steels. If you remember, we have ferritic stabilizer, austenitic stabilizer, which some alloying element stabilize ferrites, some alloying element of stabilize austenite phase into the steel. Okay, forget about that. Come to this one. Chemical property changes with change in composition. Already I have discussed you this one. Best example is same again, carbon steel to 18:10 stainless steel. Chemical property means corrosion resistance property or oxidation resistance property increases when you convert this steel into this one. But again, we'll see the physical property change with change in microstructure. If you remember from IPM class, we have talked about pure alumina, crystalline pure alumina. If you take 3 different pure crystalline alumina, and one case you have a single crystal pure alumina, in another case you have a polycrystalline pure alumina, and in another case you have polycrystalline alumina with some pores. So what happens? There is a change in properties occur. Do you anybody remember that one? What kind of properties you'll get? Change in properties. Nobody have remember?
Yes, sir.
Yes. What kind of properties will change? Optical property, right?
Optical property. Transparent, opaque.
Very good. You remember that. What is that again? In this single crystal case, you will get
Transparent.
transparency. Okay, that means you can able to read out the letters, right?
Yes, sir.
Polycrystalline silica,
So, opaque.
opaque. Okay, fine.
Translucent. Sorry, sir.
Translucent, yes. That means the letters will be visible but not clearly visible. Finally, you have polycrystalline alumina with pores, so it will become opaque. Okay. So now, do you remember how due to change in these structures, crystalline structure or some microstructures, the property is getting changed? What is the main reason behind that? How the optical property is changing?
Sir, the grain boundary are the obstacles for the light.
Obstacles, or they deflect the light, or they scatter the light so that it will not come to your eyes. So grain boundaries will scatter the light into different direction. It do not allow the light to move straight into the eyes. Changing transparent to translucent. To opaque. And porosity do the same thing. If pores will be there, pores also scatter the light. Light cannot reach to your eyes easily. One is your grain boundaries and the one is the pores. That's why it become opaque. Okay, you know that. Okay, these are some examples where we can change the properties of a material by changing the property or by changing the structure. Okay, now we'll see different microstructure phases in steel. Can you people identify? Anybody can tell me which microstructure is this of steel? Which microstructure, and which microstructure? This is of which microstructure? What you can able to see only here? Ferrite. Very good. How ferrite? Can you justify that, Mega?
Cementite phase बहुत कम अच्छी.
Cementite phase how much? No, you can see. Do you people forget? I think I have taught you about the evolution of microstructure, and I have taught you about that. I have taught you about the phase diagrams. Do you remember that? Phase diagrams, various phases, eutectic phase diagram, iron carbon phase diagram, many phase diagram I have taught you, right? So in that case, do you remember which one is single phase, which one is mixture of phase? So if you have a single phase, then the microstructure will be what? You will be having only grain and grain boundaries. That's all. Ferrite is a single phase or multiple phase or mixture of phase?
Single phase.
Single phase. That's why you can able to see only grain and grain boundaries. But what about austenite? Is it single phase, multiple phase, or mixture of phase?
Single phase.
Mixture of phase.
What?
Mixture of edges.
Austenite. I'm talking about austenite. You have forgotten the definition.
Yes, a single.
Austenite is a very, very large single phase. It is clearly visible in iron cementite metastable phase diagram. Everything is getting soluble in austenite. It is a single phase. Okay, I'll show you austenite soon. Anyways, this is a ferrite, huh? Because why? Because the grains are smaller size. That is the answer. Now you understood, people? Why? Because at room temperature, austenite forms at near to the room temperature, basically. Sorry, ferrite forms. So that is small grains, right? So this is
Pearlite.
Pearlite, very good. And this one? This is Bainite, and this is Martensite. This is a Bainitic microstructure, and this is Martensitic microstructure. You can see a large shear is there. When a Bainite Martensite forms, they are basically plate shaped in 3 dimension, and it leads to large displacement of matter, right? So okay, anyways, let me show you this image. This is from Callista. So can you people tell me which microstructure is this and which microstructure is this?
Ferrite, austenite.
This is
The left
ferrite.
side
And this is
ferrite.
how you distinguish them?
So austenite big grain ଅଛି.
Large grains. Why large grains? Why large grains? Why austenite have large grains? Hint is
Temperatures.
temperature. Yes, temperature. Because the austenite start form at which temperature? Suppose you have a pure iron, austenite will form at which temperature?
723 degrees Celsius.
723? Pure iron. I'm talking about pure iron.
Oh, pure iron. 91.
910.
91, yeah. 910, 912, like that. Anyways, above 910 or above 912. But if suppose it is an eutectoid still, then
727.
727. Very good. 727. Eutectoid temperature means eutectoid composition, 0.88%. Okay, anyways, so you understand why ferrite is small and austenite is bigger, because it forms at a high temperature. The grain become coarser at high temperature. Why the grain become coarser at high temperature? What is the mechanism? Which phenomenon is more seen at high temperature, or which phenomenon starts to happen at high temperature?
Paramagnetism.
What? Can you repeat?
Paramagnetism.
Magnetism have no role to play in the grain size. Diffusion. At high temperature, diffusion is faster, so the grain become more coarser. Okay, anyways. And this is a beautiful image of ferrite, you can see. If you remember in IPM, I have also taught you about this one. One kind of ferrite which forms along the grain boundaries. Actually, it nucleates and grow along the grain boundaries, and it cover up the grain boundaries. So this is called allotriomorphic. And this is the ferrite which forms inside the grain. That is called idiomorphic ferrite. So allotromorphic ferrites forms along the grain boundaries. Idiomorphic ferrites form inside the grain boundaries. So another interesting point I would like to say is, if some non-metallic inclusions will be there and they are present in the inside the grain, so idiomorphic ferrite will start nucleate. So that is one of the advantages of having this kind of structure. And you can see idiomorphic ferrite have a good crystal structure. It is a good shape or good crystalline shape, but this shape is not crystalline shape, right? Because they have completely spread over the grain boundaries. Okay, and this is what? This is austenitic grain boundary. But what is the exact name? Can you people tell me? This is simple austenitic grain boundary or something else? This grain boundary is simple austenitic grain boundary or something else? Prior austenitic grain boundaries, you have to remember that. Why prior? Why prior austenitic grain boundary?
Transformation starts from
Very good.
austenite.
Because transformation starts from austenite. Austenite is the parent phase, right? Then austenite has transformed into ferrites. So initially you have austenite grains and austenitic grain boundary. And on that grain boundary, a ferrite has formed. So that is prior austenitic grain boundary. So and I told you how prior austenitic grain boundaries are visible even after transformation. Why? Do you remember why prior austenitic grain boundaries are visible sometimes and they are sometimes not visible? They're visible if some pro-eutectoid phase is formed. Yes or no? Which are the pro-eutectoid phase? Pro-eutectoid ferrite and pro-eutectoid cementite. They basically form along the grain boundaries and they grow along the grain boundaries. You understood now? Next, we'll move to, okay, fine. We'll discuss about the nature of ferrite. Ferrite is basically, what is the nature of ferrite? Ferrite is soft and ductile. Ferrite is soft and ductile, right? Then we'll discuss about pearlite. So this, to explain the pearlite, I have taken water in this bucket and I have taken a cabbage. Listen it carefully. I have taken a cabbage and bucket of water. So you understand, suppose you cut the cabbage into two halves. You take one half of the cabbage and you put it into the water containing your bucket, water present in the bucket, right? So what will happen? Everybody have seen the cross section of a cabbage?
Yes, sir.
Yes, sir.
Right? The leaves are like vertical leaves. Yes or no? Leaves are vertical kind of thing. So if you put the cross section of a cabbage into the water, what will happen to the cabbage? Water will get filled up. Where it will get filled up?
Between two layers.
In between the layers of the leaves, right? Yes. So you understand. That means the moment you put the cross section of a cabbage into the water, so you understand cabbage is one phase and water is another phase. You got the point?
Yes, sir.
It will looks like one phase, then another phase is there. One another phase and another phase will be there, right? Alternate phase will be there, right? Understood now? Water is one. You can say water is one crystal, cabbage is another crystal, or one phase is your water and the phase is your cabbage. Water will be filled up in between the lips. Right? So it is the pearlite looks like this. No, it looks like this. Good experiment.
Yes, sir.
To the text, pearlite is a layer of ferrite and cementite. But this statement is a misleading statement. I told you in IPM also. This statement is a misleading statement. It is not an alternate layer of ferrite and cementite. It is basically, the definition is what?
Eutectoid mixture of.
Eutectoid mixture, that's fine. Why it is eutectoid mixture, I will tell you soon. But it is not an eutectoid. You have to tell like this, the new definition as I am saying. It is a bicrystal. Pearlite is a bicrystal. Bicrystal means two crystals. One crystal is ferrite crystal and the crystal is cementite crystal. So it is a bicrystal of ferrite and cementite interpenetrating one another. Bicrystal of ferrite and cementite interpenetrating one another. It is a continuous phase. If you take different cross sections of a steel containing pearlite, you will always end up with this continuous phase. Right? So it is not an alternate layer. It is a bicrystal of ferrite and cementite interpenetrating one another. Right? And the definition is like this: cooperative growth of ferrite and cementite from austenite. Cooperative growth of ferrite and cementite from austenite. And if somebody will ask how pearlite forms, and pearlite is a phase or mixture of phase?
Mixture of phase.
Mixture.
Yes, never say pearlite is a phase. It is a mixture of phase because it contains two different phases. One is ferrite and cementite. Okay, tell me how pearlite forms. What is the reaction? By what by what solid state reaction perlite forms? Just look at the iron carbon diagram or tell me.
Sir, austenite changes to
Ferrite.
ferrite and cementite.
What is the name of that reaction?
Tictoid.
Eutectoid.
Eutectoid reaction. You remember. Very good. Eutectoid reaction. Eutectoid reaction is a solid state phase transformation reaction. One solid is decomposing into two different solid on cooling, right? One solid is the austenite solid, which is getting decomposed on cooling into another solid. One is ferrite and the solid is cementite. So you understand this is called eutectoid reaction, fine? So during this reaction, what happens to the iron atoms and carbon atoms? Tell me. They are moving or they are constant during the transformation? When a single phase austenite will be transformed into ferrite and cementite, there is a movement of iron carbon atoms or they are fixed, they will not move.
Movement, sir.
Very little
Movement.
there will be movement of atoms. Wow, very good. You understand, because it is a completely diffusion based transformation. Perlitic transformation is a completely diffusion based transformation. Here diffusion of iron atom will occur, diffusion of carbon atom will occur. If some alloying element will be there, they will also get diffused. Diffusion means movement of atoms from one position to another position. It is okay? You have to remember this one. And another interesting point I'd like to say, so that means carbon will diffuse. So that means all the initial bonds will get breakdown. Iron atom will also move, all the initial atoms will break down and they will start partitioning. Carbon will get partitioned into ferrite and cementite. Cementite means 6.678% of carbon will be there. Ferrite means 0.0258% of carbon will be there. And austenite, you understand, that is the amount of carbon which is there, only suppose 0.8. Okay, fine. So now what is the nature of perlite? The nature of perlite is very hard phase, not exactly very hard. You can very stronger phase. It is having good toughness also. So it has high strength and high toughness. As I told, the railway tracks are made of a perlitic steels in India, basically, because they are very stronger, very hard and very strong, and have toughness also, good toughness. Why good toughness? Because ferrite is a soft phase, cementite is a hard phase. Combination of them will give you ductility as well as strength. Next we'll move. Yeah, this is a very interesting figures. These two are same. These two are same. This couple are same and this couple are same. But this is a low magnification image and this is a high magnification image. Right? These are all top images are low magnification image and this one is high magnification image. And these are the microstructure taken with help of your scanning electron microscope. FESE, it is called FESEM. Field emission scanning electron microscope. Anyways. So can you figure it out, the difference here? Anybody tell me what is the difference here? Compare all the images and tell me what is the difference you are getting from these images.
Grain size.
First tell me what are these. These are all perlites or not?
Yes, perlite.
Right? All are perlites.
Structure.
But what is the difference here?
Grain size.
Pranav is saying grain size. Okay. Anybody else? Just look at the image carefully again and again. As I told, these two images are same, but magnification is low and magnification is high. These two images are same, but magnification is low, magnification is high. These two are same, but lower, higher magnification. If you want to compare, you can compare these images. If you want to compare, you can compare these images. Don't compare this one with this one or this one with this one. You can compare, you have to do always comparison with the same magnification, right? So you can compare all the lower magnification images and all higher magnification images. Pranav is saying, coarse. Yeah.
Coarse perlite.
Yeah, let me, what you can you repeat?
So fine and coarse perlite.
Fine and coarse perlite. Very good. You have figured it out well. So, but what is the difference? Fine and coarse? How you are distinguishing them? Fine and coarse.
So first fine perlite, then second coarse.
Okay, fine. This one, right? This one and this one. Okay, very good. So how you are distinguishing them? Fine and coarse? Do you remember that I have told you in IPM? I remember. How you can distinguish fine and coarse?
जो दीटा लेयर भितर गैप टा बहुत छोटो थिबो.
Very good, very good, very good. You remember that. See, whenever you have perlites, you have perlitic colonies. Listen it carefully. Whenever you have perlite, you have perlitic colonies. Perlitic colonies means each grain is now a perlitic colony. Single colony of perlite. Means single grain is having complete perlite, right? If I will say multiple perlites means many colonies will be there, many grains. So each grain is a perlite. You understood now? Fine. But here what we can see? We can see the gap or the spacing between. This is called interlamellar spacing. Interlamellar spacing in perlite. So you understand how to measure the interlamellar spacing? Can suppose I am talking about this image. You can take the center of this one and center of this one. You just join them. That distance will be your interlamellar spacing. Similarly, here if you want to measure, you can take the center of this one and center of this one. The darker one. I am talking about the darker of the darker one to adjacent center of the darker one. Will give you the interlamellar spacing. So just look at this image is the S. Okay, fine. Let me see. B. Yes, this is moderately fine. Okay, just compare this one. Just compare these images or compare this. Better compare these images. This is a edge receipt sample. Then after edge receipt sample, suppose you are austenitizing this sample and you are doing suppose furnace cooling. So furnace cooling will give you what? Fine perlite, obviously. Or coarse perlite.
Coarse.
Coarse, okay, fine. You will get a coarse perlite, obviously. And second one, suppose you do air cooling. Fine, that is C image. This one you can see this is very fine. And when you do forced air cooling, you get very fine. This is a very fine. So fineness of a perlite is determined by their lamellar spacing, interlamellar spacing. If the interlamellar spacing is very narrow or minimum, it is fine perlite. If the interlamellar spacing is more, it is called coarse perlite. But the point is what? What happens to the strength and hardness? What happened to the strength and hardness? What is the relation?
Fine perlites ମାନଙ୍କର ଅଧିକ strength.
Yes, fine perlite. If the perlite will be more finer and more finer, the strength will increase, the hardness will increase. But what about toughness? What about toughness?
Increase.
Toughness will increase. Okay. Can you justify that, Sibasis? Yes.
Toughness is strength and ductility.
Okay, fine.
Ductility.
Yes. But
if
what
we
is
are
the relation
increasing
between
the
strength and ductility? What is the relationship between strength and ductility? Both are directly proportional or inversely proportional?
Inversely.
Inversely proportional always. If strength will increase, ductility will decrease. So, okay, let me tell you this. Okay, fine. Yeah, Sibasis, you want to speak? Yeah, you can speak.
No, sir.
The thing is what? You should remember here there will be no change in toughness. Why? Because I told you what? I told you perlitic colony. One perlite colony is a grain size. So here grain size is changing or not changing? Not changing, right? You understood my point?
Yes, sir.
The size of the grain is not changing. What is changing? The gap, the spacing between the lamellae is changing. Interlamellar space is changing. But the grain size is still fixed. Now you people understood. So instead of interlamellar spacing, if the size of the grain will reduced, then toughness may have increased, right? So you understood. So if you want high strength and high hardness, you can reduce the gap between the lamellae, right? But you cannot change the toughness by this. Okay, now we'll move to Bainite. Bainite is, you understand, we have upper Bainite and lower Bainite. These are cartoon micrographs. So this is your upper Bainite and this is the lower Bainite. Fine. You can see the difference. It is a sandwich kind of structure completely because cementite are present in between the ferrite plates. And this is cementite is present here inside the plate of ferrite and in between the ferrite. So this is the individual ferrite, and individual ferrite. So this is the difference. And I told you, if you remember, upper bainite forms at relatively high temperature, lower bainite forms at relatively low temperature, right? And this is more finer, this is somewhat coarser. If you compare them, otherwise both are fine. And this will give you more toughness and more strength as compared to this one. So what is the definition of bainite? What is the definition of bainite? Bainite is a phase or it is a mixture of phase?
Mixture of phase.
Yes, bainite is a mixture of phase. It is ferrite and cementite, right? It is visible clearly. And if you remember, bainite formed by continuous cooling or isothermal cooling? Steel from austenitizing temperature.
Continuous cooling.
Isothermal cooling, but
Yes.
directly isothermal cooling, or you have to do something initially?
No, sir. Continuous cooling, then there is a
Holding.
holding time.
Very good, very good. You have to do fast quenching. Very fast rate of cooling from austenitizing temperature to bainitic transformation temperature. And after reaching bainitic transformation temperature, you have to hold the sample for a long interval of time. So first is quenching, then that is, and the second stage is your isothermal cooling, right? Very good. And this is the real microstructure of a bainite. I think I have shown you these images earlier. Okay, anyways, tell me, this is an upper bainitic microstructure or lower bainitic microstructure?
Upper Bainite, sir.
Upper bainite. Anybody else? Anybody want to speak something? It is upper or lower? Just compare this one with this one.
Lawyers.
Black portion is ferrite.
Just look at this one at least. How you can say black portion is ferrite and a black portion is cementite? Just look at this one and tell me. Can you people identifying the crystallographic orientation? The orientation is like this: bottom to top or top to bottom, not in horizontal manner. The orientation of this bainite is, you have to remember, the bainite always oriented in a particular crystallographic orientation. This is the orientation from bottom to top. If you look at this one, this is an upper bainite, right? How upper bainite? Because you can see this lighter portion is a ferrite plate and darker portion is a cementite, right? This is one plate and this is one plate. In between them, there is a sandwich of this cementite. This is one plate and this is one plate of ferrite, right? So this is an upper bainite. It is okay now? Can you people tell me this is upper or lower bainite now? Look at the image carefully and tell me. At least tell me this one. This figure is clearly visible.
Lower bainite.
Lower bainite. How?
Some cementite in between ferrite.
Yes. Cementite has precipitate inside the ferrite plate. This is a plate of ferrite. Inside the ferrite plate, some cementite have precipitated. Right? It is clearly visible. And suppose this is a ferrite plate and this is a ferrite plate which is not clearly visible. In between them, cementite is also there. Right? So this is a lower bainite. Then this is a figure of showing martensite. Martensite, you can see large displacement has occurred. You can see large displacement has occurred due to formation. If somebody will ask what is the shape of a ferrite, you have to tell it is plate. What is the shape of a martensite? Is a plate, but tell them in 3 dimension. You understood now? Tell them in 3 dimension. If somebody will ask sometimes why this ferrite, why this bainite and martensite take the shape of a plate, do you have any idea? Okay, fine. When there will be a shear in a material, the strain will increase or decrease?
Increase.
Obviously increase. Very good. Obviously increase. So you understand, initially you have a austenite phase, and due to formation of martensite and bainite, there is a shear. More shear is here in case of martensitic transformation. You can see a lot of shear has happened. So that means shear will introduce what? Lot of?
More stress.
Lot of strain in the material, right? A lot of strain will be there in the material, right? So when there will be a lot of strain in the material become unstable or stable?
Unstable.
Unstable, definitely. So you have to remember, when martensite forms or bainite form, there is some shear in the material that leads to lot of strain generation inside the material. But to minimize this strain, there is a particular shape. It is the plate shape. That means if martensite or bainite will take the shape of a plate, there is a minimization of lattice strain. Strain can be minimized. If they have taken some other shape, like disc or some other shape, right? Then the strain minimization may not take place. You understood now the point? Because the shape of the plate shape will keep the strain less in the material. That is the answer. Okay. Then martensite. Okay, what is the definition of martensite? Can anybody remember? Tell me. This is very important. Can anybody remember the definition of martensite? Martensite is basically we call Can you tell me quickly? I have already written over here.
Solid solution of
Substitutional solid solution of
Substitutional solid
carbon in alpha iron.
Very good. Substitutional solid solution of carbon in alpha iron. But crystal structure is the crystal
Body
body
center.
center
Body
tetragonal.
center.
Tetragonal. Huh? How it forms? How it forms basically? Basically, how it forms?
Rapid cooling of austenite.
Basically, it forms by rapid cooling, or in technical term, it is called
Quenching.
Quenching.
quenching. Yes, quenching of steel from which temperature?
Austenitic temperature.
Yeah, austenitizing temperature, austenitic temperature. Very good. But do you people remember, if after quenching you will get an martensite, do that still have application, direct application? Hmm? Nobody have remember? This is the answer. What I have written.
No direct application.
Yes. So after quenching the steel, if you are getting martensite, you cannot apply that steel for direct application. Why? Because it contains a lot of internal stresses. That is one part. But main part is the steel is behaving as a brittle nature. It will easily break. Or the plastic deformation will not happen. It will easily get cracked. Brittle means, you understand. Brittle means low toughness. Low ductility. It is okay? Now you people got the point? This steel has high strength, but problem will be what? The toughness is very low. So do you remember, if the toughness will be very low, what will happen to the steel? It will easily break into pieces. It get easily fractured, right? Because it will not absorb a lot of energy, because there will be no more plastic deformation will happen here, right? So the point is what? Finally, we can convert the martensite into tempered martensite. Tempered martensite forms by, this is formed by tempering heat treatment. We'll discuss that. What is that treatment? Treatment after hardening heat treatment. Fine. So tempered martensite name comes from because after tempering you are getting a martensite that is called tempered martensite. Can you people figure it out? What is happening? Here you can see needle shaped, but basically 3 dimension it is plate shaped. But what is happening here? Okay, what is the composition of? Okay, what is the composition of martensite? What is the composition of martensite? Anybody remember?
It 0.76% carbon.
What you are saying? I haven't told about anything 0.7. Have I told you the composition of initial steel?
Nice, sir.
Then how you can say 0.7?
Sir, Pearlite.
Just read it what I have written.
There is no phase change.
There's no phase change. Phase has changed,
Phase
na?
transformation. Sir.
No composition change.
Austenite has become ferrite. The phase change is there. But during this transformation, what has happened? Just read it what I have written.
Diffusion less transformation.
Yes. So you understand what has happened? What hasn't happened?
Yes, diffusion hasn't happened because
Diffusion
of very
that
high
means-
rate of cooling.
That means the carbon which is getting dissolved in the austenite has already there in the martensite itself. It hasn't migrated anywhere. You understood now? Means
Yes, sir.
no diffusion of, you can write no diffusion of iron atom, carbon atom, and any other alloying element, any other substitutional alloying element. So can you people figure it out? What is the difference between then Pearlite transformation and Martensitic transformation? What is the main difference?
Diffusion of carbon and iron atom.
Very good. Yeah, diffusion of. Tell it clearly, Pranav. You are saying right, but tell it clearly.
Diffusion of carbon and iron atoms.
And if other alloying element will be there?
Yes.
Yes. So that means that is why Pearlite transformation is completely diffusion based transformation, whereas Martensitic transformation is a diffusion less. And this kind of transformation you have to remember is called displacive transformation. I will tell you that soon in the next class maybe. Displacive transformation, and Pearlite transformation is called reconstructive transformation. Okay, fine. We will not discuss much here.
Manila ma'am link pathayilani.
Okay, sorry.
Manila ma'am.
Okay, you can wait for 5 minutes. So what can you people tell me? What are these white substances? In this particular microstructure, carbon is getting trapped in the ferrite. That leads to formation of BCT, body center tetragonal structure. Carbon do not diffuse. Why carbon is not diffusing? Can anybody tell me?
Due to very high rate of cooling.
Due to very high rate of cooling. That means carbon is not getting time to diffuse out. Very good, very good. So now what is happening? Can you tell me what are these things then? These are cementite particles, right? These are cementite particles, and this darker portion is your ferrite. So tempered martensite contains what? Ferrite matrix. Ferrite matrix with lot of dislocations. Ferrite matrix with lot of dislocations. Tempered martensite means ferrite matrix lot of dislocation. Plus, what will be there? Tell me quickly. This matrix is ferrite now. And this one is?
Cemented.
Cemented particles. Very good. Cemented particles are of which shape now? It has taken a shape of spherical shape, basically. Spheroids. So tempered martensite contains a ferrite matrix containing a lot of dislocations, and on that matrix we have cemented particles of spherical shape. This is called tempered martensite. Can anybody tell me why this has happened from here to here? That means in this process diffusion has happened or not?
Yes.
Diffusion has happened. Very good. That's why they are forming spheroids. Particles are coming closer to one another and becoming spheroids shape, right? So diffusion has happened here in this case. So tempered martensite, so that means, and if you understand, ferrite matrix is a soft phase or a hard phase?
Soft.
What about cemented particles?
Sir?
What about cemented particle nature?
Brittle.
Yes. So brittle or it is hard and brittle? Which one is most important? They have taken a spheroidal form. They are not needle shape now. So I have written this structure is having high strength and toughness and well ductility. You got the point how? Because this matrix is a ferrite matrix which is soft, but due to the dispersion of these cementite spheroid particles, they have good toughness value, and the brittleness have reduced, and internal stress have removed, and ductility is good. So finally, this kind of material can be used into the application part. It is okay now? Okay, last slide, you can see this one. This is an image of your spherodite, and this is an image of tempered martensite. Sorry. This is spherodite. Spherodite means the cementite has undergone spherical forms, basically. That is called spherodite. And here it is a microstructure showing tempered martensite. What is the difference? You have to remember the difference is in tempered martensite, the similarity. First, let me tell you the similarity. In this similarity, both have same ferrite matrix. Listen it carefully. Both have same ferrite matrix and cementite particles. That is the similarity. But difference is what? The difference is in spherodite, you can see this white phases or lighter phase. Lighter phase means no dislocations. A very small amount of dislocation is present. But here you can see very dark portions. Very dark portions. That means it contains lot of dislocation here. That is one difference, right? So tempered martensite have a lot of dislocation in the ferrite matrix, but it do not have, or less amount of dislocation density will be here. And the difference is the shape. The shape, you can see the shape is basically polygonal. The cementite particles are polygonal, or they are basically, some are spheroid. You can see some spheroids, some are polygonal, and some are like small bar shape, right? But here, basically, they are spheroid. In tempered martensite, the cementite particles are spheroid shape, basically. So this is the difference between them. But this one is having high ductility, but this one is having high strength. That is the difference. Okay, I'll stop here. If you have any doubt, you can call me or you can text me if you want.